Okay, so this is the first problem of today's contest, and in this problem we are given that we have a sequence A1 to AN and a sequence B1 to BN is called good if it satisfies these three conditions. So the first condition is that BI is a positive integer from 1 to n, then BI is not equals to AI for any I from 1 to n, and BI is a strictly increasing sequence. So we can solve this problem, like we have to finally find the minimum value Bn among all good sequences B1 to Bn, like the whatever good sequences exist, out of all of those sequences we have to find the minimum value of Bn that there is. So how we can solve this problem? We can just see B1 can be 1 if A1 is not equal to 1. If in case A1 is 1, then our second option for B1 will be 2. Like this way, we can maintain a variable x as 1, and for each bi, we'll try to give it x if ai is not equals to x. Otherwise, if ai is equals to x, we'll first increment x by 1 and then give bi as x. And after giving bi x, next time for the next iteration, we anyway have to increment x by 1 because bi should be strictly increasing sequence. If we follow this method, the last value like bn that we get is the minimum possible. Is it okay? Yes, no, anything? Okay, it's clear. So let me show you the implementation. So this is the implementation. In this, I have first taken n as input, then I've taken array a as input. So this is the final vector b. You don't actually need to create this. You just need the final value, but I have taken it. Then initially my x is 1, then I'm going from 0 to n minus 1. You don't need a while here. You can also do an if. Like this is okay. A of I is equals to x. So in that case, you'll increment your x by 1. Then you will insert this at the end of your vector b. And for the next iteration, you'll increase your x by 1. So if you follow this method, the last element in vector b is your smallest, like the minimum value of bn possible. So let's go to the next problem. In the next problem, we are given, that we have n sets of integers s1 to sn. We call a set S attainable if it is possible to choose some, possibly none of the sets s1 to sn, so that S is equal to their union. Now, if you choose none of s1 to sn, their union is an empty set. So this is just the definition. Like if we choose some, then we'll get like S is attainable if, like after choosing some sets S1 to Sn, their union, like S is nothing but their union. And if we choose nothing, then S is an empty set. So we have to find the maximum number of elements that there can be in an attainable set S, such that this attainable set S is not union of all of these. So let me tell you the problem statement here. See, there are some sets S1, S2, and S3. There are some elements in this set, some elements in this, and some elements in this. There may be some elements common, like one is present in every number. This is having 4, this is having 2 and 3, this is having 5, 6, and 7. So first of all, S1 union S1 union S2 S1 union S2 union S3 is nothing but 1, 2, 3, 4, 5, 6, and 7. So we are given that we have to find a maximum, like a attainable set S, which is union of some of these S1, like some of these S's, some of these sets. We have to find a set which is union of these sets and is not equals to this thing. So how to do this? See, and see, first of all, the problem statement is clear, right? What we have to do.
Yes, sir.
Okay. So finally, the set that we are looking for, if this is the like union of every set is this thing, so the set that we are looking for, like it should at least not have this thing or this thing. Like at least one of these should be missing in my final set, right? Yes, no? Like the final maximum element number of, like maximum number of elements attainable set that I'm looking for, it should at least, like either it shouldn't have this element or it shouldn't have this element. These are the elements which belong to this set, S1 union S2 union S3. So this final set should either shouldn't have this thing or this thing. Like it should not have at least one of these, right? Yes, no?
Yes, sir.
So
Yes,
why
sir.
not, since there are only 50 values, why not try for each of these? First, let's say if one is in this set, like if one is present in this set, that is union of S1, S2, S3, I'll try to find a set, I'll try to make this set, assuming that one will not be in my final set. So what do I need to do? There are some sets S1, S2, S3 till Sn. If S1 is having one, then I'll exclude it. If S3 is having one, I'll exclude this, and I'll take union of these two. If I do like this, I'll get a set, and my answer will be nothing but answer will be maximum of answer, comma, the number of elements in this set, number of elements. Then I do the same thing for 2. If 2 is present in this set, that is union of every set, then I'll exclude those sets which are having 2 because I don't want 2 in my final set. And then for all the remaining sets, I'll take their union and I'll again take the answer as maximum of answer, comma, element. So I'll do this for every element from 1 to 50. Finally, I'll get the answer. Is it clear? Yes, no?
Sir, but how can we say that in this set which has all the elements, so
Yes.
excluding only one element will give the answer? Like it is possible that two elements are not in the whole union.
Yes. So basically, I'm just saying one element shouldn't be there. If 2 elements are not there, then eventually you'll get answer using this only. In that case also, at the end, there should be at least one element which is not present in your final set, right? So I'll try to remove only one element. If there is a case in which I'm getting like there's only a case in which there are 2 elements missing, I'll get that also using this. Because if there is a case in which 2 and 3 are both missing, I'll remove 2, 3 will also get removed. Because maybe 2, when is this possible? When 2 and 3 are both coming from only one set. If 2 is
Okay,
coming,
okay.
so
Yes, sir, got it now.
so is this clear to everyone, or does anyone wants me to repeat this? Otherwise, I'll show you the implementation. Is anyone having any doubt?
Hi, sir.
Yes.
I have solved this problem using recursion, but when I try to memorize it, my solution is giving wrong answer. Pick not
Okay.
pick
So
approach I have implemented in this
you
question.
you had different approach than this.
Yeah.
Okay. So I'll like probably after, like I won't be able to debug your solution right now in the like in this session.
Oh, all right, sir. No, thanks. Fine.
No. Listen to me. So there is no like you can just raise a query and tag me in it. After this session, we can have a meet, and then we'll try to see whether like is there an implementation mistake or is your approach wrong. Okay.
What is your name, sir?
You can like Ankit. You can.
All right.
Okay. So let me like take second test case. If it's not clear, like it will be clear then. So this is the test case. Let's take this thing. This is the test case, right? So the first set is having 1, 2, 3, and 4. The second test case is the second set is having 2, 5, and 6. The third one is having 3, 5, and 6. And the fourth one is having 4, 5, and 6. So can anyone tell me what is the union of each of these? Like if I take S1 union S2 union S3 union S4, what I'll get?
1, 2, 6.
Okay. So now, first, if you don't want 1 in your set, then you won't take this set and you'll take everything else. So you'll get 2, you'll get 3, you'll get 4, you'll get 5, you'll get 6. So I think the answer is, for this case, it should be, the maximum should be 5. Is it 5? Yes, it is 5. So you get my point, right? So in this case, we are getting directly here. But if you don't want 2 also, then you won't take this, and you'll take these 2. So in that case, you'll get your set as 3, 4, 5, and 6. So the size of this is just 4. The size of this is more. So basically, your answer is 5 here itself. Is it clear? Yes, no. Okay, so I'll show you the implementation. So this is the implementation. In this, I have first taken n as input, then I have taken, these are the all the sets, n sets. So all for this is vector of vector is for all the sets. Then I have taken a count, which is telling me whether ith element will be in my like union of everything or not. You don't need this up till 100, you just need this up till 51, because there are at max like the element that will be there is 50. I took it 100 because it won't give you TLE or MLE. So just for like being on the you don't actually have to take this, you can take this 50. But anyway, so then I'm taking all the set as input, and for each and every set, I'm incrementing my count. Like this element is present. You don't actually have to increment this. You can just do something like this element is present, I think. Yes. So you just have to make sure that this element is present in the final set. So you can do something like that. This element is present. Like this element will be present in your final union of everything. Now this is my answer. This is another count. Like this is for if I don't have like some of the sets, then like for the remaining sets, if I take union of those, which all element will I get? So first, like I said, like you don't actually have to go till 100 again. You can just go up till 51. So for each of the numbers between this, and again, you can start from 1. Like I think in the problem statement, numbers are from 1 to 50 only, right? Yes, the numbers are between 1 to 50. So that's why you can start from 1 to 50. And first look that if this element is not present in the final elements, like if this element is not present in union of every set, union of everything, then you can simply continue. Otherwise, first make everything in your count to vector as 0. Now iterate through all the sets. Now this binary search is an intern STL function. So if I'll simply search whether this ith element is present in VJ set or not. Since VJ is already given to us in sorted order, that's why I can simply do this, that if this element is present in ith element is present in this VJth set, then I'll simply continue. That is, skip this set. Otherwise, I won't skip this set. I will take every element of this set and mark that element as 1 and count 2. Finally, my answer will be maximum of answer, comma, every element, like how many elements I'm getting if I don't include any set which is having this ith element. So this is that thing. I'm just finding the count, like sum of the ones in count 2. Finally, I can print my answer. So is it clear? Yes, no? Like the
Yes, sir.
implementation is a little messy, but you get the basic idea, right? What is trying to be done here. So let's go to the third problem.
Yeah.
Yes, yes.
Hello.
Yes.
Can you explain the accumulate wala part आप explain कर सकते हो?
Okay. Accumulate. See,
Hello.
basically for every element from 1 to there are 50 elements, right? So for for all of these 50 elements, I'm just trying to first see if the ith element is currently present in this set. I'll skip this set. Otherwise, if it is not present in this set, for every element of this set, I'll mark like everything is 0 initially in count 2, right? So I'll mark it as 1. Now, what do I have? See, in count 2, everything is 0 initially. then for some sets I'll be marking like I'm getting 2, so instead of 0 there will be 1. I'm getting 4, 1, so I'm getting 5 also, then 1. So finally how many elements I'm getting? If you find the sum of all of these like vector, sum of this vector, you're getting 3 elements. So that's why I'm using accumulate. It is just all sum of all the elements of count to vector. Is it okay?
ठीक है भैया.
Same thing with this fill. Fill is nothing but like I'm trying to make every element of count to as 0. Is it okay now?
Can you
Yes.
repeat how to take the input?
Like input is simple. Like first you take n, these are the number of sets, then these are the 3 elements. In first set there are 3 elements, in second set there are 2 elements, that is given by this 2. In third set there are also 2 elements.
Okay.
Is it okay? Is it okay? Yes, no?
Yes.
Okay, so let's go to the next problem. So this is the next problem. In this problem, we are given that we have n cards stacked in a deck. Initially, AI is written on the ith card from the top. The value written on the card does not change. So now we will play a game. Initially, our score is 0. In each turn, we can do one of the followings. If we choose an odd integer, we will remove that card from the deck. We will add the number that was written on that card to our score. Now, this is done only when we choose an odd integer, odd positive integer I. And then like the remaining cards will be re-indexed. Otherwise, if we choose an even integer, everything's like same thing will happen, but now we won't add this number to our score. So finally, like, and we can stop anywhere in between. Like we can stop the game anywhere. Like we don't have to remove each and every card. So we have to find what is the maximum possible score that we can get. So let's take -4, 1, -3, 5. Let's take both of these. Okay, let's take everything. So this is the example. So the first example is -4, 1, -3, and 5. So see, if we remove this thing is an even, right? This is an even. So you will just remove this and this won't add anything to your score. Now after this, you will get -4, -3, and 5. So now if you remove this thing, this is the third index, right? So you will get 5 as in your score. So for this test case, you can prove that this is the most optimal score that you can get. So first of all, did you get the problem? Yes, no? Did you get the problem statement? Like what do we want?
Yes.
Okay. Yes, it's one based indexing. So let's take another example, 1, -2, 3, -4. In this problem, we can just, like in this test case, we can first take this, since this is odd, we'll have 3 in our score. Then we'll get 1, -2, and -4. And then we can take this. So we'll have 3 plus 1. So that is 4. So how to actually solve this problem? See, there are just 2, 3 cases. The first case is, assume the first value itself is positive. Like anyway, like we'll try to take all the positive values and we'll try to skip all the negative values, right? Because we want to have maximum score. So we'll try to take all the positive values and skip all the negative values. So how to do this? See, if the first value itself is positive, this is the odd. So after this, let's assume that negative values are not existing. So some of the positive values are at odd place. I'll write O for odd and E for even. So something like odd, odd, even, even. These are all the positive values. I'm not considering the negative values now. Some random order, okay? I'm just telling you that we can take every positive value. So
If the first position is positive, then we can take every positive number.
yes,
Is it?
yes.
Why?
Like I'm explaining why. Just give me a minute. So see, if this is like first positive element is like the first element is positive. So what I'll do, see, the last is odd, right? So I can take this. Yes, you can take this. Then this one is even. So you'll take the first next odd. If you take this odd, this will get shifted by one place. This will again be like this even will become odd. So you'll take this also. This is odd itself. You will take it. This is even. So you'll take the next odd before it. You'll take this. This will become odd. You'll take this. This is even. This is even. This is even. So you'll take the first odd next to these. This you'll take this. Now all of these even will become odd. You'll take this odd, this odd, this odd. This is odd. You'll take it. This is odd. You'll take it. So do you get my point? If you're getting any evens, you'll try to see what is the odd before all of these. And there will always be an odd because the starting position is odd itself. Once you take that odd, all of these will become odd. And now you'll take these in left, like right to left order. Because going from right to left, if you take first this, the parity for this won't change. So do you get my point now?
Yes, I got it.
Okay. Is it clear to everyone? Like not just to this? Is it making sense for everyone? Like if we start, if the first place is having the odd value, then we can take everything.
Like, except the first one, every position is moving between odd and even, odd and even.
Yes, and
Is it correct?
you can somehow take everything, right?
Yes.
Now let's suppose the first one is negative itself. The first one is negative and the second one is also negative. So now you have something like maybe something. So now if first one is negative and the second one is also negative, so what you can do, see, you can just remove this thing. Why? No, okay, don't remove this thing. If you remove this thing, you'll get negative. You can remove this thing. Why? See, if your first starting, like first positive was at odd place, then the problem statement is same as earlier. Why? Because all these earlier were negatives, and basically you can assume that your array is starting from this place. So it is same. But if your first place was even, then you can remove the second negative. Why? Because if you remove this, you won't add anything to your answer, and now the first positive will be at odd. So in case your first and second both are negative, then also your answer is like you can get every positive. Yes, no, anything?
Can you repeat this part?
Okay, I'll repeat this. See, we have taken that case that when first element is positive, then you can take all positives. So what is this first positive? What, like, now assume that the third one was like the first positive is at third place, the first two are negative. So then also you can assume that your array is starting from the third place only, right? Ignore these two. Like what is this first place? This is odd. So for if your first element, basically this is if your first positive is at odd index, and this is one based index in one based. So if this is like if your first positive is at odd index, then you can get all the positive values. Is it making sense? Yes, no? Like just ignore all the values which are before the first positive, right? Here there were no values, here there are two values. So what is the difference? But let's suppose that your first positive is at even index. Now let's not take it as this two, anything other than two. So let's say fourth. So you can remove this second element, right? You can this is also negative, this is also negative. You can just remove this second element. Now everything will shift one time, like one place to the left, and the first element which was earlier at even place, now it will come at odd place. So the same thing is applicable, right? Yes, no.
Yes, yes.
Okay. So there are two cases. If the first is positive, then or if first and second both are negative. So in both of these cases, your answer is you can take everything. You can take every positive element. Now there is only one case left. Can someone tell me what is the case which is left in these two? The first is negative, and the second is positive. Right? Only this case is left, right? Yes, no.
Yes.
Okay, so what is actually happening in this case? See, if the first one is negative and the second one is positive, and then there is something going on here. So eventually we will be able to take everything that is positive here. Why? Because by the same rule, if the first positive in this part is at odd place, we can take it by the same rule. But if it is not at the odd place, it is at even place, then we can first remove this, but we won't get, in this case we are not actually getting this in our score, but everything in this part we'll be getting, right? Yes, no.
Yes, yes.
But there is one case in which we can get this positive, but along with this positive, we'll also get this negative. How? Can anyone tell me? First, you take this negative, so you'll get this much in your score. Why? Because this is at the odd place. If you remove this thing, now this will come at the first place. Then you take this thing. So now you'll get this positive element because this is at the odd place. So you will get this thing together. You cannot get this alone, this first positive, if it is at the second place, right?
When the positive one is greater than the negative one.
Yes, yes. So basically, if the sum of these two is positive, or in other words, if this positive is more than the absolute value of this negative, so you can add that to your result of this thing. Is it clear? All the three cases? Yes, no?
Yes,
Yes.
yes, clear.
Okay. So that is what I have implemented here. See, first I have taken n as input, then I have taken array a as input. Then if n is 1, in that case, you can just simply check if the first one and only value is negative, print 0. If it is positive, print it and simply continue. Now array elements are, at least there are two or more elements. So check if the first element is itself positive, or if the first element is not positive, it means it is negative. So by default, this statement, like, okay, let me write this completely. If first element is positive, or a of I is less than equals to 0 and end. So this is the complete statement. Like if the first two elements are both negative, or just the first element is positive, then we can have every positive element. So just add maximum of 0 or this element in your answer and print it. Now the one case is left in which first element is negative and the second element is positive. So in that case, you can have every element from 2 to n minus 1 and just add maximum of 0 and the sum of first two elements. Then you can print answer. Is it clear? Is it clear to everyone? Yes, no, anything?
Yes.
Okay. So let's go to the next problem. So in this problem, we are given that we have a tree, and we have a tree with n vertices labeled from 1 to n. All integers ai are like an integer ai is written on vertices from I to n. Now we want to make all ai equal by performing some possibly zero spells. So suppose we root our tree on some vertex. Now on each spell, we can select any vertex v and any non-vertex c, like any non-negative integer c, and then for all the vertices I in the subtree of v, replace ai with ai XOR c. Now the cost of this spell is s into c. C is the integer, non-negative integer that we selected, and I've like the c is the non-negative integer that we selected, and S is the number of vertices in the subtree of this vertex on which we applied our spell. So we have to find the number of, like, the cost of making every element same, assuming we root our vertex, like we root our tree on ith vertex and I will go from 1 to n. So let me explain this problem here. See, forget about routing your tree to other places. Assume that you have something like this thing. Let's take the first example itself. So in first example, I think it was something like this. And then we have 3, 2, 1, 0, 3, 2, 1, 0. These are the A values. And then we have 1, 2, 2, 3, 2, 4, 1, 2, 2, 3, 2, 4. So these are the vertices. So now let's say this is our root, okay? This is our root. And I have to find what is the value required to make, what is the cost, minimum cost required to make all the values same. So first of all, see, the observation that is required here is, if you want any subtree, like if you want, let's say this is your tree, if you want all the values same, like for this node you want every value to be same in its subtree. So first of all, everything in this node's subtree should be equals to this. Why? Like all of these three should be same. Then if these three are not equals to this, then you can have one operation and make these three equals to this. But first of all, these three should be equal, because if these three are not equal, whatever operation you perform on this, even if you make this node same as this value, you won't be able to make these two equal to this. So these, all the three should be same for first of all the three values in this subtree should be same. Then you will perform one operation on this node, and if you make this node equals to this, by default all the values in this node, like in this subtree, will be equals to this node. So similarly, if like I said, if you want this subtree equals to this node, then you'll have to make everything in this subtree same, right? So you'll have to make these two nodes also equals to this. So what is the number of operations, like the cost? It is nothing but, like, let's say we have A of j written on this node, A of I written on this node. So we'll have to perform, what is C? C is the XOR that I will perform on this node. So C is nothing but AI XOR AJ. If I perform like operation using this C, then I'll get AI on this node. Is it making sense? Yes, no?
Yes, but can we instead also do like from top to bottom?
Yes, you can do it like that also. So now this is the seed that you will choose. And by the way, how many subtrees, like how many nodes are in the subtree of this? It's just one. So the total cost will be C, that is this value, that is AI XOR AJ into number of nodes in the subtree of this. So it is nothing but 1. So similarly, you will compute for this thing and you will add this value to this node, because for this node you are having all these operations. So finally, when you are at this node, again, when for this node, how will you look at this? Now let's say this is the kth node. So the value is AK. So again, you will do value for node K will be value for node K will be, if let's say I is the child, value of I, like whatever value, like whatever cost was up till subtree of I for making all the nodes in subtree of I same, plus A of I XOR A of J into nodes in subtree of nodes in subtree of J I, like why this will be K. This is AK into AI. So this is XOR of AK into A of I. Like this is the number. If AK and AI are same, this will be 0 only. Then you don't have to do any operation. But if they are not same, this is the C and this is the number of nodes that like this will get multiplied. So are you getting why I have done this? Is it clear? Yes, no? Like if anyone is having any doubt, unmute yourself and like let me know what is the part that you're not getting. This is value.
Clear.
So now what we can do, we can just root your tree at any node. Let's say we root our tree at node 1. And for node 1, we are not calculating for every node. We are just calculating for node 1. For node 1, we can calculate, right? For if let's say this is u and this is node v. So for node u, we can just do for every node, like every node u. Like if there is an edge from node u to node v, then what we can do, value at node u, we'll add value at node v. That is everything, like what was the cost for making edges, like nodes same in subtree of v, plus if a of u is not equals to a of v, then this is the value of c that we will use into subtree of v. Like what are the number of nodes in subtree of v? So in this case, it's 2, right? There are 2 nodes. So using this, we can get the answer for node 1, right? Yes, no?
Can you explain one again?
Like which part?
Like how we will find for u after v?
You'll simply, like this is DP on trees basically. And DP on trees plus rerouting, what I'm doing. Rerouting I have not done till now, like we'll do it in a moment, like how we will do reroute. But first of all, this is just simply for this value, you'll calculate from here, but in order to get the value from here, you'll have to go here. So you'll calculate, like first go down there, DFS, you'll DFS down here. Then in order to calculate for this, you'll have to go down again. So this is just a
Yes, okay, got it. Like
leaf
I
node.
thought for u node you are finding final answer.
No. So then you'll go down, this will be 0. Then you'll return back, calculate for node V. Once you have calculated for node V, you'll go back, then calculate for node U. Like before calculating for node U, you would have gone in each of the nodes in subtree of node U. Is it clear? Yes, no?
Yes,
Is
it's
it
clear.
okay? So now once you have done, so you have some tree, you already have answer for this node. So now you just have to make root this. How to make root of this? First of all the, like, let's say this is count as the number of children for this node. So let's say this is count v, this is count u. So how to make this as your, there are 2 things, value and value v and value u. So how to make v as node? First of all, how much this node contributed to this thing? I'll subtract it. Okay, let me get it here. So value of u, I'll subtract like whatever was the contribution earlier. Value of v plus what was the contribution? A of u XOR a of v into count. Count is the number of nodes in the subtree of v, count of v. So first I'll decrease this thing, then I'll update the count values also. Now count u is minus equals to count of v, because this is not like v is now no more in subtree of u. So count u minus equals to count of v, then count. Now u is now in subtree of v. So count of v plus equals to count of u. Why? Because now u is up in subtree of v. V is the root. So now I'll update the value of v. Value of v, this is v. Value of v is nothing but value of v plus equals to value of u plus same thing, a of u XOR a of v into count of u. That is the number of nodes in the subtree of u. Is it clear? So now V will be the root. So this is just rerouting. If you're in level 4, maybe this will be taught to you if it has not been taught. So this is
Can you
rerouting.
explain once again rerouting part?
Okay, you are in level 4, right?
Yes, but still not
So
taught.
this, okay, this is not taught, or is this has been taught, rerouting?
No, like still till now it is not taught.
Okay, it is not taught. So rerouting is basically from this, if this was your root, you're trying to shift to this. So there are some parameters. So in this case, it's value and count. So first undo whatever the contribution was for node V from node U, and then add contribution of node U to node V. So this is removal and this is addition.
Okay.
Like assume that U is now no child of V. So like this is just putting this in brief, but like there is much more to rerouting than this. So once this is done, this will be the root of the tree. And after this, like you'll keep shifting your root to every node. And finally, you'll get the answer for every node using DFS. So like it will be much more clear once I show you the implementation. Just give me a second. So this is the implementation. In this, I have first taken n as input. Then I have taken array A as input. Like these are the values of each thing. This is the tree. Now first I have to count the nodes in every subtree. Like for each node, I have to find the number of nodes in its subtree. So this can be done using just simple DFS. So just increment U, like for each node, increment count U by 1y, because this node will be in its subtree, right? And when you're calling DFS, first call DFS, and then for each node, add the number of all the nodes which were in V subtree. If U is parent of V, then all the nodes that were in subtree of V are also in subtree of U. So this part is clear, right? Counting the number of nodes in each subtree. Yes, no?
Like in this
Yes, someone was saying something.
like we are adding count of V, but count of V itself will include count of U when we take U V as a root.
Like nothing is root here. Like just for if U is parent of V, then the number of nodes which are in subtree of V will also be in subtree of U.
Okay.
And root is basically this 0 on which I have called DFS. Now this another DFS function is calculating answer for this root, assuming this is the root. So how is it done? For every node U, if V is the child, so I have to just add value of V, whatever cost was in subtree of V, plus this thing, what is this thing? Number of nodes in subtree of V multiplied by this thing, XOR of these two. So after this, I will have the answer calculated for node 0. And then there is this second DFS function, which is basically the rerouting part. So what is rerouting? See, first of all, answer of U for every node, answer of U is value of U. Now, for when I'm going to any child node, first of all, decrease the contribution for current node. Like this is decreasing the contribution. I've done it in 2 lines. You can do it in 1 line. Then update the count values, like how many nodes are in subtree. Then now give the contribution to node V. Earlier, like we removed from node U, and now we are adding to node V. Then call the DFS function. Same thing will again run. Once you return from that step, now again make node U as the parent node. So this is just like this part is just reverse of this thing. I've just, if there's a plus here, there's a minus here. So it is plus plus plus, then there is a minus. Like I'm just doing the reverse of this thing to again make the node U as the parent of node V. Finally, once we return from this function, we can print answer. Like answer is nothing but for each value, what is for each node, what is the minimum cost to make every node same, every node have the same value if ith node was the root of the tree. Is it clear? Like have you, like forget about the implementation, maybe you can implement this in a better way, but are you getting the idea how to solve this problem? Yes, no?
Yes.
Okay. So that's it for today. And thanks for
It will
joining.
be
Bye-bye.
thought.
Just wait for a second. Let me stop the recording.